This is Software Engineering Radio, the podcast for professional developers, on the web at se-radio.net. SE Radio brings you relevant and detailed discussions of software engineering topics at least once a month. SE Radio is brought to you by IEEE Software Magazine, online at computer.org/software.
Nathan Marz, welcome to Software Engineering Radio. Today we're talking about distributed computation with Apache Storm. So why don't we start off by talking about the problem that Apache Storm solves in the abstract. So I guess maybe we can start off by just defining streaming.
Sure. Well, let me start off by just talking about what motivated me to build Storm in the first place. So I was working at a startup called Backtype at the time. We were doing real-time analytics of social media data. So we would do things like we could tell, like one pretty straightforward thing we did is we could tell businesses stats about their Twitter presence. So for any URLs they tweeted, how many times was that tweeted or retweeted in total across the entire Twitterverse. And so the way we were doing our real-time portions at that time is we had a set of queues and workers that would do the processing and interact with the database while they were doing the processing. And we found that this became unwieldy as our real-time processing became more complicated. So for example, like we would have the entire Twitter fire hose on a set of queues, and then we'd have one set of workers maybe do some initial analysis on the tweets and maybe write the tweets into our Hadoop cluster, and then they'd have to pass whatever they process to another set of workers to then update, let's say, a Cassandra database with the stats. And we found that we'd have one application, but the actual implementation for it would be split among many workers, and we'd have to coordinate how do the workers talk to each other, how do they serialize data. And we found that our actual business logic only ended up being a small portion of our code base as compared to all the coordination logic. So Storm was initially conceived as a generalization of the queues and workers paradigm, so that you could build applications in one program and have it run on a cluster of computers and be a lot simpler to both write and deploy.
And so was that a pretty difficult process to separate the specific Twitter application from the sort of abstraction that Storm ended up being?
I mean, the way I go about designing software is I do everything based on concrete use cases I have. So I had a lot of different analytics use cases. I also had some other real-time use cases, such as we were computing this. We were doing this computation called reach, where we would take a URL and we would tell you the number of people, the unique number of people ever exposed to that URL on Twitter. So to do that computation, you have to take the URL, get everyone who tweeted it, get all the followers of everyone who tweeted it, and get the unique set of all those followers. So for something like a TechCrunch URL, where let's say 10,000 people tweeted it, you're dealing with that follower set of millions or tens of millions of people, which you then have to unique and count. So it's not something you can do fast on a single machine. It's something that you have to distribute. And that this was one of my real-time use cases that I had been thinking about at the time. And I do this process when I design software where I try to unify my use cases into a simple set of abstractions, and that's where Storm came from. When I looked at this reach problem and I looked at these different streaming analytics problems, I realized that there was this very simple set of abstractions which would be able to handle all those cases very elegantly. And that's how I initially came up with Storm. It just happened to be that those abstractions happened to be very general purpose.
And so just to motivate some more examples for throughout our conversation, just at a high level, what are some other applications that you've seen Storm successfully deployed on? So there's Twitter, analytics, and then so what are some other examples?
There's so many. That's actually been one of the most rewarding things about making this project is just seeing all the industries using it, which it's hard. It was hard to anticipate exactly who would use it. Some of my favorites, well, probably my all-time favorite company that uses it is not so much for what they're doing with it, but more who the company is. The Weather Channel uses Storm.
Interesting. Oh, that's great. It totally fits the name.
I just love that. I remember when I got that email, I was so happy. It made my week. But yeah, it's used heavily by Twitter. I mean, I'm most familiar with the things I used it for. At Twitter, we had lots of analytics applications. We had lots of discovery applications. So a lot of the Twitter Discover page is powered by Storm. It's doing like real-time machine learning and real-time clustering to find out what stories would be interesting for people to see. It's used by some health companies. So one of the weird things about doing a big open source project is that people use your project very heavily, but as the product creator, I actually don't get that much insight into the details they're using it for. So most of what I know is, it's being used in this industry for this general category of applications. But if you look at like Storm's powered by page, it's used by like WebMD, Spotify, Flipboard, Alibaba, Baidu, Yelp, all sorts of companies in completely different industries. There's financial applications.
And so do you think prior to them starting to use Storm, they were just sort of doing the same thing that you were doing in terms of just, kind of, figuring out their own sort of system and then they realize like, oh, our in-house solution is way more complex than the solution would be if we modeled it in terms of Storm?
That's my feeling, yes. Certainly I know before I created Storm, the way people did real-time processing was very ad hoc and not very robust. It's a pretty hard problem to actually really make stream processing robust. And that's something that you largely get out of the box with Storm. So I think that was one of the major motivators for people to adopt the project.
What are those problems that make it so hard?
So I guess the key problem is getting a guarantee of data processing in a simple way. So you're processing a stream of data. How do you guarantee that everything that comes through there will be processed? Because you have to handle the fact that any worker can fail at any point for any reason. So the way you do this with queues and workers is that between every set of workers, you have queue servers, and the queue servers actually persist any messages that come to it to disk. And the idea is that if when a worker processes a message, it doesn't actually take the message off the queue until it's successfully processed the message. So you have this thing called an ACK protocol where you take the message from the queue, process it, and then you acknowledge it, and then the queue drops the message. Now, the problem with this approach is that it's actually very complex because you need to persist all your intermediate messages. And so you have to, that's like a whole nother thing that you have to worry about scaling and making working. And so Storm is able to get that message processing guarantee without any intermediate queues. And it does that via this algorithm I developed, which is really the key to Storm and the heart of what makes it go.
Could you talk a little bit about that?
Yeah, sure.
I don't know how, or if that would be, maybe too into the weeds, or maybe you can just sort of discuss sort of the key insights into how you provide these guarantees.
I can give a high level on that. Let's start with just what like a Storm application is. And
sure, yeah, we could zoom out and come back to that. Maybe we can start. We can talk about the the three abstractions that are really important in Storm, which are spouts, bolts, and topologies.
Yeah. So basically, a Storm application is something called a topology, and it's just a graph of computation. And there's two kinds of elements in that graph. The first is called a spout, and a spout is a source of streams, and all a stream is an unbounded sequence of tuples. And so spouts do things like they'll read from a queue server and they'll emit that as a stream. And And then you have something called bolts, and a bolt consumes any number of input streams and then produces any number of output streams. And a topology is just a network of spouts and bolts. And one of the keys to Storm's abstractions is that everything there is inherently parallel. So kind of like in MapReduce, where you write a mapper function and a reducer function, but then they execute in parallel across many nodes. It's the same thing on Storm. Spouts and bolts are parallel. They run across many nodes. And the connections between them just indicate essentially a stream subscription.
Okay, so and just to reiterate, to give the listeners maybe like a mental image of how this looks. The topology is the graph as a whole.
Yes.
The spout is like the source of streams. So that would be if you're maybe going from a queue server maybe to the recipient, or I'm not sure if I'm grasping it right, but if you're going
let me give an example.
Sure, that'd be great.
So like an incredibly basic example. So let's say you're doing that thing I was talking about of computing the number of retweets that every URL on Twitter has received. So let's say that you keep that stream in, let's say, a Kafka queue. And then you'll have a spout, and Storm actually comes with a Kafka spout implementation that can expose that stream for processing in your Storm application. So you have your Kafka spout emitting this stream of tweets. And then you would have a bolt that would subscribe to that stream of tweets, and it would subscribe to it using what's called a fields grouping, where you partition the stream by the URL field. So that would mean that every tweet of the same URL would go to the same Storm worker, but different URLs might go to different workers. This is a way that you can distribute the processing of the tweets, but have the data partitioned the way you want it, where any URL is processed by at most one worker, or by exactly one worker.
So is a spout analogous to a producer, and a bolt is analogous to a consumer? Yeah,
that's a good way to think of it. Except bolts can also output their own streams as well, which other bolts can subscribe to.
Okay.
Yeah.
So it's not completely accurate to think of spouts and bolts as just what's the word? Not vertices, but the arrows between vertices.
Edges,
right. And so it's not completely accurate to just think of spouts and bolts as directed edges. They're sort of edges and nodes.
Yes.
Okay.
I think of the edges as being the streams that are flowing between your processing components.
Okay. All right. Interesting.
Yeah.
So maybe we could circle back to that the question I asked earlier, which is getting into a little more specifics about the algorithm that makes. It sounds like it's very important to making Storm tick, and it's as I understand, it's the algorithm that ensures, I guess, like consistency and reliability across these queue servers.
It ensures reliability, so it just guarantees that every message that comes into a Storm topology is successfully processed. And so basically the way it works, or the best way to understand it, is actually look at like what does data flow look like in a streaming application. So basically you start off with the spout, and it emits some tuple. And then that tuple goes to some bolt, which then looks at that tuple and then creates new tuples based on that tuple. And then those new tuples go to other bolts, which create tuples based on those tuples, and so on and so on and so on. And so that initial tuple, that one tuple coming off the spout, triggered this entire tree of computation that occurs on your entire cluster. And so Storm calls that the tuple tree. So every tuple that will eventually be generated based on that original input tuple. And the way Storm defines that a spout tuple is successfully processed is whether that tree is completely created and processed within a specified timeout. So if that condition does not occur, let's say after 30 seconds, that spout tuple is considered failed and it needs to be replayed. And so what Storm does is it actually tracks that tuple tree for you and detects these conditions and then tells the spout whether the tuple succeeded or whether it failed and needs to be replayed. And when you first look at the problem, the way you think about doing this is to track the tuple tree explicitly. So actually keep track of which tuples are still in flight and which tuples have been finished processing. But then you get in the problem there is that you don't really know how much memory you'll be using because you have no idea how large the tuples will be or how large the trees will be for these tuples. And so the key insight in Storm is that I figured out a way to do it such that it only uses about 20 bytes to track a spout tuple, regardless of how big the tuple tree gets. The tuple tree could have 1 billion pending messages, and it still only needs 20 bytes to track the tuple tree.
Wow, that sounds like quite an accomplishment.
Yeah, you definitely need visuals to actually see how to really understand it fully. It's actually really well explained on Storm's documentation.
Sure.
If you just search like on Google Storm guaranteeing message processing, you can read a page which goes in depth on how the algorithm works.
Okay, sure.
Yeah, it's based on random numbers and XORing. It's a pretty cool algorithm. It works by making a probabilistic trade-off, such that there is a small chance that it'll make a mistake. But it turns out the chance of that mistake is so incredibly low that you can basically ignore that. Like I think a Storm cluster, if it were processing 1 million messages per second, it would make a mistake. I think it was once every 10,000 years. So it's the kind of thing which you really don't have to worry about. And so that small trade-off in making this, pseudo probabilistic algorithm gets you massive resource savings.
Interesting. Is there any? I mean, if you somehow like scaled Storm, let's say you scaled like a single Storm cluster to work off of and you had this Storm cluster working for all of Google's processing and Amazon's processing, like all the data processing in the world. Does that continue to hold true, or does it? Do you start to have like more collisions or more?
Man, that's a really good question. Is how many messages are processed per second on the whole world? It's probably a lot. But the nice thing is that algorithm. All you have to do is if you just slightly increase the amount of like. So I said use about 20 bytes. If you were to use 30 bytes to process messages, I don't think there's any amount of processing that you could physically do that would ever cause a random failure.
Okay, yeah, I mean it's probably pretty narrow question, but whatever.
But basically, the more bits you're using for those random numbers you generate, then the less the chance of a random failure goes dramatically down.
Okay, sure, makes sense. Yeah. So part of one of the motifs. You see if you explore the Storm site, the main website is Storm aims to do for stream processing what Hadoop did for batch processing. Mm-hmm. So maybe you could characterize this statement a little more, and because I'm curious if are there tasks that people perform in batch that might be better off, like they would work better if people had like engineered them in a way that allowed them to be streamed.
So what I mean by that statement is that Hadoop provided, or just more MapReduce in general, it provided a simple way to think about computations that could execute scalably and reliably. And the key there is simplicity. So as a user, you didn't have to worry. You didn't have to constantly be on guard for all these like concurrency traps or how to make things fault tolerant. And all of that stuff. It's just a simple, as long as you stick to the MapReduce paradigm, right, you can do scalable batch processing.
This is like at the highest level, the nomenclature that the programmer has to work with is you have a mapping function and a reducing function.
Yeah.
Similarly to like the vocabulary that you have with spouts, bolts, and topologies.
Exactly. And so that's what I mean when I say Storm does for real-time processing, what Hadoop did for batch processing. It provides a very simple set of primitives that gives you the guarantees you need without it basically what I'm saying is it massively lessens the burden on the programmer to make this stuff work. And Storm does that for real time, and I think Hadoop did that for batch processing. And as for your other question, you were asking, are there things that people are doing in batch that are better done in real time? That's kind of a hard question to just answer in the abstract. Obviously, if you're trying to use Hadoop to make things real time, that's not going to work very well. But I don't think many people are actually doing that. I view batch processing and real time processing as very different, and I view them as working very well in conjunction with each other. I actually wrote an entire book about this, about how do you think about big data problems. How do you think about attacking any big data problem? It turns out there's very general techniques you can use that combine batch processing and stream processing and give you very simple, elegant solutions.
Are there some patterns of that you could discuss?
Or
is this does this get into like a Lambda architecture?
Yeah, that's the Lambda architecture.
Okay, interesting.
Which is actually very commonly mischaracterized. Like, it's not as simple as, like, just because you're using batch processing and real-time processing does not mean you have a Lambda architecture. But basically, at a high level, the Lambda architecture just starts with a general formulation of, like, what is a data system? Like, what are we trying to do at a fundamental level? And the way I define it is that the most general purpose data system you can think of computes functions that look at every piece of data you've ever seen. And it computes those functions in real time. So a query is a function of all data. That's where you start. If you can build a general system, if you can come up with general techniques for implementing any function of all data in real time, then you know how to attack any problem. And that's what the Lambda architecture is. The Lambda architecture is an architectural pattern for computing functions that take in your entire data set as input and return the result in real time. And just at a very high level of how it works, or just the general ideas behind it, the idea is that you have two layers. You have a batch layer and a real-time layer. And the batch layer literally computes functions of all data. Like, that's the power of batch processing. That's the power of MapReduce. That's the power of Hadoop, is that you can compute a function that looks at your entire data set at once. And so what you do in the batch layer is you run a function on your entire data set, and you produce what are called batch views. So this is an indexed data set which you can use to do reads for that query quickly. So let me ground it with an example. Let's say you're doing let me use an analytics example. You're doing something like Google Analytics, where you want to know the number of page views to a URL over a range of time. And so your batch view might look at all your page view events you've ever seen and then produce an index from URL and our bucket to the number of pages for that bucket. And it's an index that you can query, you can do random reads on. And so the nice thing about, if you just look at just the batch layer, it actually satisfies almost every property you'd want of a big data system, except for one. And some of those properties are, it's really robust. If you ever were to deploy a bug which corrupted your views, you always have the power to recompute those views from scratch because everything exists in a batch processing system. It's completely scalable. It's very easy to implement. It's very easy to debug. The one property it does not have, though, is that it's not fully up to date because batch processing is a fundamentally high latency operation, so those views are going to be out of date by a few hours. And so that's where the real-time layer of the Lambda architecture comes in. The point of the real-time layer is just to compensate for those last few hours of data, so just to fill in that gap. So the real-time layer is where you might have, let's say, a Cassandra database, and then you process the stream of pages as they come in, and you keep track of the pages over time just for the last few hours. And the idea is that as the batch layer catches up to the real-time layer, you can discard the stuff that's now captured from the batch layer. So it keeps your real-time layer very small, and therefore much easier to manage.
Interesting. Yeah, I think we're gonna be doing a show soon on Lambda architecture, and I definitely look forward to hearing more about that topic. So, and one thing that you mentioned is the ability to sort of roll back and replay something, like if something goes wrong. And I the last show that I did was a show on Kafka with Jun Rao, one of the one of the people who's contributed a lot to the Kafka project, and that was something that he mentioned as a great feature of Kafka, is that if something goes wrong, you can replay pretty much whatever you want to. So is I know you mentioned that as a feature of the Lambda architecture as a whole. Is that a feature of Storm?
So Storm does make use of that in Kafka. So the way Storm. So I talked about Storm, how Storm guarantees data processing, and it does that by if there's ever a failure in the processing of a spout tuple, like anywhere in the cluster downstream from where that spout tuple was emitted, it will replay that spout tuple or that tuple from the spout. And ultimately, like your spout implementation needs to coordinate that with whatever queue server it's using, so it's able to know to do the replay. And so the basic Storm, when you're just talking about spouts and bolts and processing messages one at a time, it's very simple. If with Kafka, it just keeps track of the offset it's successfully processed in Kafka, and until it won't actually move its offset until all messages between the new offset and the old offset have been successfully processed. Now, one thing that Kafka enables, just by the nature of the queue system, is that thing you were mentioning, where you can go back and replay stuff that you may have already successfully processed. It's hard to get into on a podcast, kind of the technical details of this,
Sure.
But basically what that property enables is the ability to do exactly once processing semantics. So the basic Storm API that you get from one at a time streaming with spouts and bolts, you get at least once processing semantics. But with something called Trident, which is an API on top of Storm, it doesn't do one at a time streaming. It does what's called microbatching, and it makes use of that property of Kafka to give you exactly once message processing. So even if while you were processing one of those micro batches and you were updating a database and you only updated like some parts of the database and you failed to update other parts of the database, it will replay and then when it retries the update to the database, it will be just like you only ever did it one time. It's really powerful. It was a very difficult problem to solve, to get real time exactly once semantics, and that's largely built off of that property that you're able to get from Kafka. Again, this is very hard to explain on a podcast, all the technical details.
Of course.
It's very well explained on Storm's documentation of how this works. Yeah.
Okay, so this will put the discussion into a little more tangible terms, or workable for a podcast. But so let's say I build a service like Twitter, mm-hmm. and I'm doing like real time streaming across the service, and I've got my Storm cluster working. It's going great. I can do all kinds of things like calculate the number of people that are sharing a link, stuff like that. And so suddenly I get like the huge surge in user growth, mm-hmm. and my Storm cluster is not able to keep up. So what are the type of symptoms of a Storm cluster that is that's suddenly not able to handle the load? Like let's explore that topic and sort of the problems that might start to occur and how you debug the system. So what might start to happen?
Well, first of all, if you ever got in that situation, you've done something seriously wrong. Okay. Storm is one of the focuses of Storm is operationalizing real-time processing and making that easy. And so Storm has a huge focus on metrics and measuring. So when you're running a Storm cluster or like a Storm topology, you should know like how much of a surge it can take, or at what scale can it run. So like if you basically if you got in that situation, then you have not been properly looking at the metrics and planning for future growth. But basically, if you got into that situation, what would happen is that you would notice that your queues are backing up. So Storm is not able to keep up. So the offset of where Storm has actually processed into your queue would be way behind what's actually in the queue. This is one of the basic things that we would monitor in Storm is how far behind is it, and of course we would have alerts whenever it gets too far behind.
Sure. Okay. And so let's say we see that we need to we're good Storm users and we're realizing we're going to need to add some more servers to keep up. So is scaling a Storm cluster just as easy as kind of hooking up some more servers and then I think there's like a rebalance command. You can just do rebalance and
yeah.
How does that work exactly? How does the rebalance
It's
command
basically
work?
that easy. You would add. Well, you need more resources. So you would add nodes to the cluster, and then you would increase the parallelism settings of your topology. So you'd figure out where is it getting bottlenecked, and then you would increase the parallelism there. Storm tracks this really cool metric for you called capacity, where it measures for a bolt in the last 10 minutes, what percentage of that time was actually spent in the processing function for that bolt. So if that approaches 10 minutes, then that means that bolt is saturated. It literally cannot, it's not possible for it to handle any more throughput because there's no more time left to process any more messages. So, one key, that's a key metric you look at when you're operating a Storm cluster is make sure your capacity numbers are kept well below 1 so that you can handle surges in traffic or handle more throughput coming in.
Do you know if a lot of people that are building Storm clusters are they doing so on hardware that they have in the building, or are they doing it on something like Azure or EC2 or Google App Engine or I guess Google Compute, whatever the equivalent is for that? Like, are they building it? Are they building it on hosted solutions, or are they doing it locally?
People are doing all of the above.
Okay.
I don't know exactly what the percentages are. Certainly when we initially created Storm, we were running it on AWS because that's how we did our infrastructure at Backtype. Then when we got acquired by Twitter, we were using Storm on internal hardware. I know that Microsoft recently announced that they are supporting Storm on their cloud product, which I thought was really cool. So, yeah, it's running in all scenarios and all platforms.
Cool. Okay, so kind of continuing the topic of things going wrong, how does Storm deal with just sort of simple failures, just like if a node goes down or there's like a network partition? What typically happens?
So if a node were to go down, then Storm would reassign those workers to other machines. And likely what's going to happen in that case is, let's say you were to kill -9 a worker, then there will be messages in flight that were meant to be processed by that worker, which will now not be processed. And so that will cause those spout tuples to time out, and they will be replayed, and they will eventually go to the new worker that spun up on some other node. So that's actually really straightforward. A network partition, basically those workers would become isolated from Storm's master, and so they would die, and then Storm would, again, just create those workers on a node that is actually reachable by the master.
And tell me about the Storm, like the daemons. There's Nimbus and then the supervisors.
Yeah. Storm cluster is composed of it's composed of 3 components. The first is Nimbus, which is the master. And Nimbus is who you talk to when you want to deploy a Storm topology. And Nimbus will allocate resources for the topology, assign workers in each node to process it, and it will monitor the cluster and reassign workers if they were to fail. Then in the middle, you have a Zookeeper cluster. So, for people out there who are not familiar with Zookeeper, that's actually a different open source project, which is really good for distributed cluster coordination, which is exactly what Storm uses Zookeeper for. And then you have a set of supervisor daemons. You run one supervisor daemon per node, and the supervisor daemon just communicates to Nimbus through Zookeeper to determine what should be running on that machine, and then it will start and stop workers as necessary, as dictated by Nimbus. One cool property of Storm's daemons, this was actually a key design point, is that they are what I call process fault tolerant. So you can kill -9 Nimbus or the supervisors, and nothing will happen to running topologies. This was a key. I worked really hard to get this property for Storm because I had a lot of experience with Hadoop, and back then Hadoop did not have this property. If you killed the job tracker, all your jobs were dead. And for real-time processing, that is obviously completely unacceptable because you're supposed to have basically 100% uptime. And so basically, as long as the Nimbus process restarts within a reasonable amount of time, you're not going to have downtime for your cluster because basically when Nimbus is down, you lose the ability to reassign workers, but the workers that are there will keep on running. So if Nimbus comes up in 30 seconds, then you've now 30 seconds later regained the ability to reassign workers.
So is the case, are the daemons set up sort of that the worst case scenario, absolute worst case scenario, you're not making progress, but you're not going to have a dirty result. You're going to just have no progress?
No. You're still making progress. The workers are still running.
Oh, okay.
You can deploy a Storm cluster, deploy a topology, and let's say it assigns 10 workers for that topology, and then you kill Nimbus and you kill all the supervisors. The workers are going to still sit there doing the work and processing. While your daemons are down, specifically while Nimbus is down, you've lost the ability to reassign a worker that fails. But as long as it doesn't fail, it'll keep on running. Obviously, you want Nimbus and your supervisors to stay up so that you have that fault tolerance. But the point is that if they were to fail, and there's lots of reasons why a process could fail. One common reason is that there might be maybe there's a bug in Storm where it has some random null pointer exception. But then the process fails and it restarts and it just picks up where it left off and it keeps on working fine. I think processes dying. So the thing about streaming is that you're trying to make applications that run for months without needing before you redeploy it or update your application, and you want it to have 100% uptime for all those months. And it's very difficult to guarantee that a process will not fail 3 months later. Like, who knows what state your JVM will be after 3 months of constant usage? It's very hard to say. But when you have process fault tolerance, you have the ability to restart processes without affecting or without destroying your running application. And that's the property you get with Storm's design. Like one common way we would use that process fault tolerance is in Storm development. Is I'm able to take an existing cluster and then kill Nimbus and do upgrades to it, actually change its code without actually affecting the running cluster. Like, that makes things so much easier from an operational standpoint, especially when you have one-off bug fixes you need to deploy, and you're able to do it without having to take everyone's applications down first.
Great. Okay, so let's talk a bit about how Storm is differentiated and maybe how it's synergistic with other frameworks that are in the same area. So maybe we could talk a bit about how Storm interacts with, or maybe it just replaces things like Kinesis or Spark or Samza or Kafka, whichever of these sort of other areas you think are relevant to the discussion. Or I know you already mentioned Kafka, so maybe that's a good place to start.
Yeah, well, Kafka and Storm are very complementary. Kafka is basically, you should think of it as a message queue. It's a multi-consumer message queue, and so it's a very good piece of technology to use to feed a Storm cluster with streams. I'm actually not that familiar with Kinesis, but from my general understanding of it, Kinesis is competitive with Kafka. I do know that the Amazon guys built a Kinesis spout, so you can use Kinesis to feed a Storm cluster. I think other technologies which you can actually compare to Storm, or which are in some ways competitive to Storm, are things like Spark and Samza. So Spark is actually a good comparison point because I kind of view there as being three major paradigms of computing that have emerged over the past years. The first is batch processing, where you take a static data set, a very, very large static data set, and you run a function on that data set. Then you have stream processing, or let's say, all right, let's call it stream processing, where you process messages as they come in. You look at them one at a time, and you do that processing with very, very, very low latency. And then the third paradigm is a hybrid of those two, which is called microbatch processing, where you don't look at messages directly as they come in, but you process them in small batches. So maybe you look at a few seconds of messages at a time, or maybe half a second of messages at a time. Spark does batch processing and microbatch processing. Storm does microbatch processing and stream processing. And where these paradigms differentiate themselves is with the guarantees they can provide and the latencies they provide. So with stream processing, you can get very low latencies. Like we're talking about millisecond level latencies, but you can only get an at least once processing guarantee. With microbatch processing, your latencies go up to half a second or 1 second or a few seconds, but then you can get an exactly once processing guarantee.
So are you saying that there is there's almost it sounds like there's a continuum between batch processing and stream processing, and then and somewhere along this continuum there's something called microbatch processing.
I wouldn't say it's continuum. I'd say there's just three paradigms and microbatches in between. Yeah, it's just the nature of how these algorithms work and what is. It's really just. I mean, I've thought about these problems for a really long time, and it just comes down to what are the limitations of nature when it comes to how we can process things and what guarantees we can get. I don't think there's anything between microbatch and stream processing in which you would trade off the guarantees in a different way. Like that's just how the guarantees play out.
Okay.
Yeah.
And so.
But let me continue.
Sure. Go ahead. Yeah, go ahead, please.
Yeah. So basically, like again, we're talking about Spark. So Spark does batch and microbatch, and Storm does microbatch and streaming. So if you have an application that really needs low latency and needs streaming, then that's not a use case Spark was built for, but that's a use case that Storm is great for. If you have an application that wants to do iterative machine learning in batch, that's something that Spark is great for, that Storm is not built for at all. And then when it comes to microbatch, which they both do, they also differentiate themselves there as well. So Spark is really focused on keeping state within the cluster and internal, which has a lot of use cases on its own, especially when it comes to things like machine learning. Whereas Storm is really focused on Storm itself being stateless, but then interacting very nicely with external state, like databases like Cassandra or Redis or whatever you're using. So when Storm does its exactly once guarantees, that's writing to a database which you then may use to serve applications the way you normally use with a database. So Storm is about exactly once. When it comes to microbatch processing, is about exactly once with external state. Spark is about exactly once with internal state.
Okay.
Yeah.
And so, in terms of maybe an more of an actual application type of scenario, so like if we go back to the example of the Twitter stream or the Twitter application, just how fast are streaming platforms able to move events through a system? So is this fast enough that it appears synchronous to a human user at a browser? So if I do something, in Twitter, and then let's say there's some other part of Twitter that's that event. Let's say I do something on Twitter, and that event has to move through the Storm computation or the Storm cluster, and then I'm seeing the result on my Twitter dashboard or whatever, how long does this take, or is it like very quick, or maybe you could characterize this?
I just in the applications that my team built on top of Storm, some applications we were getting end-to-end latency of less than 30 milliseconds.
Wow.
Yeah, and I talked about like that reach application, or that reach computation where you have to take your URL, get all the people who tweeted it, get all the followers, and then unique that set. And the only way to do this fast is to parallelize the computation. That's a really intense computation, and basically in terms of and that's something I call distributed RPC. We're using Storm, where you kind of think of the input stream as a stream of function invocations, and the output is a stream of results of those functions. And so you can use Storm as this RPC server where it computes these functions in real time, in parallel across a Storm cluster. And so when we initially had reach at Backtype running just, being done by a single node, doing all those database fetches and computations, like some of those reach computations would take like over a minute to run. And when we moved it to Storm, it would only take 2 seconds. And that was actually synchronous. Like you're literally just doing an API call. You say, get me the reach for this URL, and then it returns you the result. But that processing all went through a Storm cluster to do the parallelization. That's a really intense computation. There's a lot of distributed RPC computations which don't have to look at tens of millions of elements at once, in which case you'll get latencies on the order of 30 milliseconds, like I was talking about before.
Yeah, so to drive home this point, could you define again the distributed RPC?
Yeah, so just think about it as like RPC, remote procedure call, where you query some other server with a question, like what's the reach of this URL, or give me the top 10 search results for this search query. And it turns out there's a lot of problems, or there's a lot of problems where it's hard to compute these queries just on a single node. So like in the case of reach that I was talking about, the problem is that there's just so many database calls you have to do and just so much data you have to sift through to do the uniquing and the counting. It's just slow to do on a single machine. So distributed RPC means that you implement your function as a distributed application, and then you coordinate that when that distributed application emits a result, that you're able to send that result back to whoever actually requested it. And so this is first class in Storm, this notion of distributed RPC. So it's very easy to build applications in which you can implement your processing as a Storm topology, and then have the result automatically sent back to the user who actually asked for it.
And just so we can get another couple definitions or another contrast that I think is important in this domain, I read a really good core answer you gave where you talked about the difference between real-time processing and stream processing. So maybe you could kind of reiterate that discussion.
I'm actually not sure what I actually said on that core answer.
Oh, okay, sure. So whatever your current thoughts are on the difference between real-time processing and stream processing.
Well, I mean, that's a very almost pedantic discussion.
Oh, okay.
Like real time, if you look at academia and papers, the way they use real time is different. Like their definition of real time is just that you guarantee that some computation will finish before a certain time, which is, I think, different than the common usage of real time. Like they would consider something, I mean, as far as I understand how they use the word, they would consider something real time even if it were to finish 10 seconds from now, as long as you guaranteed it would finish in those 10 seconds. And I think their notion of real time is that you take real time into account when you're planning computations.
Okay, that is pretty pedantic.
Yeah, and whereas I think the common usage of real time is just that you're doing stuff with very low latency. And so that's when I've used the word real time, that's what I mean when I use that word.
Okay, so maybe the contrast between real time processing and stream processing is not totally productive.
No.
Okay, so maybe we could talk a little bit about well, let's see. I'm trying to think of what we haven't explored. Let's talk a bit about the programming aspect. So the programmer sits down. What does he have to what does the program have to understand? What is the client API?
So
I guess aside from the programmer sits down, he knows the definition of a spout and a bolt and a topology, but
Yeah.
what does he sit down and do?
Yeah. It largely depends on the programmer and what language they're working in. One of the nice things about Storm is that it was designed from the beginning to be able. You can write Storm applications in any programming language, and so at its core, all of Storm's bolts and spouts and topologies are actually defined as thrift structures, and I don't want to get into thrift, but the basic takeaway from that is that thrift is this technology that lets you define those data structures using any programming language, and so that's what enables you to build Storm applications on any programming language. Now, if you're working in a language like Java, which is what Storm is implemented on top of the JVM, then you basically have an interface for spouts, which has three main methods on it. First method is just give me the next tuple in the stream. Another method is this tuple that you emitted before has been successfully processed. And then the last method is this tuple you emitted before was not successfully processed and you need to replay it. Then for a bolt, you just have one method which takes in an input tuple and then is expected to emit any new output tuples that the bolt wants to emit to its streams. And then you have the topology, which is literally just a graph where you just hook up spouts and bolts, and you say who subscribes to which streams. And that's it for the basic Storm spouts and bolts API.
Sure.
Yeah.
Okay. So I guess how can our listeners find out more about you or the future of Storm, or what are some good resources that you'd suggest for our listeners?
Well, to find out more about me, I have a website, nathanmarz.com. I'm also on Twitter at nathanmarz. As for Storm, so Storm's an Apache project. We actually fairly recently became a top-level Apache project, which was a really cool milestone to hit. We have a website for Storm, storm.apache.org. And also there's a Twitter account for Storm at Storm Processor. So those are the best ways to keep up with the project. We have very active community and very active mailing lists. So there's both a user mailing list and a dev mailing list. And if you look at those resources, you can see what the roadmap of Storm is and where we're headed.
Is there anything else you would like to mention regarding Storm or distributed computation or just anything from our discussion?
I guess the last thing I can point listeners to is I wrote this really long blog post about the history of Storm. I learned a lot building a project of this scale, both in terms of like the technical challenges I had to face, but also in terms of the scale at which just the number of people using it. It was a really interesting learning process for me, and I tried to capture a lot of those lessons in that blog post. And so that's on my website. It's called History of Apache Storm.
Yeah, I mean, I'm kind of curious about that. Just as somebody that works on, just projects on the side sometimes. I mean, maybe you could, I guess, cap us off by talking a bit about that experience of like how did you, almost in terms of like, having the will or I guess putting yourself in a position where you're thinking about ways to build projects on your own, because I think this is actually like something that's pretty important is like how, as a programmer, when you're building your career, you always want to be thinking about things that you can do on the side to sort of like level yourself up. So maybe you could talk a little bit about that.
Yeah. Well, so when I look at Storm's success, I realize that for any project to be successful, there's two aspects to it. First of all, is it has to do something useful from a technical standpoint. But the second aspect, which is just as important, is that you have to convince people that your project is the best solution to their problem. And I think what many, if not most, developers fail to understand is how difficult and interesting that second part is. like I learned so much about communication and how to get people to understand the problems it is you're trying to solve and why that's useful for them. Which basically that is marketing. That's what marketing is. A lot of programmers view marketing as like negatively because they think of marketing as all those like stupid advertisements you see on TV. Marketing is just about getting what's in your head into the head of your potential users and convincing them that what you're doing is useful. And so a lot of lessons I learned is how do you do that effectively.
Yeah, and I see that in the succinctness of the API and also from almost like your first principle of like, okay, how can I translate the MapReduce or how can I learn from the MapReduce paradigm and build these like really simple to understand abstractions so that people can communicate easily with each other what Storm is and what Storm does.
Yeah, well, certainly having simple APIs and simple abstractions makes that process a lot easier. And when it came to communicating Storm to people, I definitely took advantage of using Hadoop as a starting point for explaining Storm, because a lot of people went through the grueling effort before me of getting people to understand the concept of MapReduce and batch computation. And by making analogies to that, I was able to, in many cases, short-circuit that process of getting people to understand Storm's ideas for real-time processing.
Right.
Yeah.
That's great. All right. Well, Nathan Marz, it's been a pleasure interviewing you about Apache Storm. Thanks for coming on the show.
Yeah. Nice talking to you.
Yeah, it was great talking to you.
Okay. Take care.
All right. You too. I'll see you.
Bye-bye.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more information about the podcast, including other episodes, visit our website at se-radio.net. To support us, you can advertise SE Radio by clicking the Dig, Reddit, Delicious, or Slashdot buttons on the site, or by talking about us on Facebook, Twitter, or your own blog. If you have feedback specific to an episode, please use the commenting feature on the site so that other listeners can respond to your comments as well. This and all other episodes of SE Radio is licensed under the Creative Commons 2.5 license. Please see the website for details. Thanks again for your support.